Somewhere in the constellation Scutum, roughly 19,000 light-years away, there is a star so impossibly vast that if you placed it where our Sun sits right now, its surface would swallow Mercury, Venus, Earth, Mars, Jupiter, and keep going until it engulfed Saturn's orbit. Astronomers call it Stephenson 218, and it is often described as the biggest star ever discovered. Its estimated radius is 2,150 times the width of our Sun. Its volume could contain 10 billion copies of our star. But here is the part nobody tells you. That record-breaking measurement rests on a foundation so uncertain that some researchers believe the number could be drastically wrong. The most terrifying thing about the biggest star is not its size. It is the fact that we are not even sure how big it really is. If you enjoy journeys into the most extreme and unsettling corners of the universe, do me a favor and hit that like button and subscribe. It costs you nothing, and it helps this channel bring you more stories like this one. Now, get yourself comfortable. Let's begin. Somewhere in the back of your mind, you carry a simple idea about stars. You learned it as a child, maybe from a poster on a classroom wall, maybe from a documentary narrated by a calm voice over sweeping animations. The idea is this: stars come in different sizes. Some are small, some are medium, some are enormous, and somewhere out there, one star is the biggest star in the universe. A single object holding the ultimate record, the champion. You imagine it sitting on a throne of fire, dwarfing everything around it, and you assume that astronomers have found it, measured it, confirmed it, written the name down in a ledger, case closed. That assumption is wrong. Not slightly wrong, fundamentally wrong, because the story of the biggest known star is not a story about a clean measurement and a tidy record. It is a story about a bloated, dying colossus sitting 19,000 light-years away in one of the most obscured regions of the Milky Way, a star whose very identity has been debated for decades, whose distance remains uncertain by more than 50%, and whose famous size estimate conflicts with the theoretical limits of what stellar physics says should be possible. The star is called Stephenson 218, and the journey to understanding why it became the most famous giant star candidate on Earth requires starting not with the star itself, but with the deceptively simple question that made it famous. What does it actually mean to call something the biggest star? This question sounds trivial. Biggest means biggest. Largest means largest. You measure it, you compare it, you rank it. But in astrophysics, size is not a single number. Stars can be compared by mass, the total amount of matter they contain. They can be compared by luminosity, how much energy they radiate. They can be compared by temperature, the heat of their visible surfaces. And they can be compared by radius, the physical distance from the center to the outer edge. These properties do not scale together in simple ways. A star can be extraordinarily massive without being physically large. Neutron stars pack more than the mass of our Sun into a sphere roughly 20 kilometers across. A star can be enormously luminous while remaining relatively compact. Some blue supergiants outshine the Sun by millions of times while maintaining radii only 30 or 40 times larger. And a star can be physically enormous, stretching across billions of kilometers of space, while being surprisingly low in mass compared to its sheer volume. When people talk about the biggest star, they almost always mean radius, physical size, how far the star extends from its center to its outermost visible layer. This is the measurement that produces the jaw-dropping comparisons, the animations where Earth shrinks to an invisible dot beside a stellar sphere that swallows entire planetary orbits. Radius is what makes the story dramatic. And radius is exactly the property where Stephenson 218 makes its most extreme claim. But measuring the radius of a distant star is nothing like measuring the radius of a planet. You cannot photograph the disk of a star 19,000 light-years away. You cannot see its edge. You cannot place a ruler across it. Instead, Astronomers must infer the radius through indirect methods that depend on knowing other quantities first. If you know how luminous a star is, meaning how much total energy it radiates in all directions, and you know its effective surface temperature, you can calculate its radius using a relationship rooted in fundamental physics called the Stefan-Boltzmann law. A cooler star of a given luminosity must be physically larger than a hotter star of the same luminosity, because its surface radiates less energy per unit area and therefore needs more surface area to produce the same total output. This relationship is elegant. It is reliable when your inputs are accurate, but if either the luminosity or the temperature is wrong, the radius you calculate is wrong too. And for Stephenson 218, both inputs carry serious uncertainties. The luminosity depends on knowing the distance. The temperature depends on interpreting a spectrum that is partially obscured by thick dust and expelled material. Every derived property of this star rests on a chain of assumptions, and the chain is longer and more fragile than the headline number suggests. None of this was obvious when the story began. In fact, for the first decade after its discovery, Stephenson 218 was not famous at all. It was barely noticed. It appeared in the data as a bright infrared source near a cluster of red supergiants, one dot among many in a crowded and dusty region of the galactic plane. Understanding how it went from an anonymous infrared point to the most discussed giant star candidate in popular astronomy requires going back to a survey conducted in the late 1980s by a careful and methodical American astronomer named Charles Bruce Stephenson. Stephenson was not looking for record-breaking stars. He was conducting a deep infrared objective prism survey of the northern Milky Way using the Burrell-Schmidt telescope at the Warner and Swazi Observatory. Infrared surveys are essential for studying the inner regions of our galaxy because visible light is heavily absorbed by interstellar dust. The thick clouds of gas and debris that fill the galactic plane block optical telescopes from seeing most of the stars that inhabit the spiral arms near the galactic center. Infrared radiation passes through this dust far more effectively, revealing objects that are completely invisible at shorter wavelengths. In 1990, Stephenson published a short paper reporting the discovery of a cluster of faint, dust-reddened stars in the constellation Scutum. He described 10 objects, several of which appeared to be M-type supergiants, concentrated in a small area of the sky roughly 1.5 by 3 arc-minutes across. He estimated that the cluster lay approximately 30 kiloparsecs away, roughly 98,000 light-years, based on the assumption that the stars were all red supergiants with typical absolute magnitudes. This distance would have placed the cluster far beyond the galactic center, deep in the outer reaches of the Milky Way. The discovery attracted little immediate attention. The paper was brief, the objects were faint, and the estimated distance was enormous. The cluster was catalogued and filed away. It would take more than a decade for astronomers to revisit these stars with better instruments and realize that Stephenson's distance estimate was dramatically wrong, not slightly off, wrong by a factor of 5. In 2001, a team of researchers began re-examining the cluster using near-infrared photometry and found that the stars were much closer than originally thought. By 2007, a detailed study led by Ben Davies and collaborators determined a kinematic distance of approximately 5.8 kiloparsecs, roughly 19,000 light-years, using the radial velocities of the cluster members compared to models of galactic rotation. This placed the cluster not in the outer galaxy but in the Scutum-Centaurus arm, one of the Milky Way's 2 major spiral arms, near the intersection with the northern end of the galaxy's central bar. The cluster was renamed RSGC-2, short for Red Supergiant Cluster 2, reflecting its nature as one of several massive open clusters in Scutum, containing large numbers of red supergiants. The revised distance changed everything. Stars that appeared moderately luminous at 98,000 light-years became extraordinarily luminous at 19,000 light-years. The cluster turned out to be one of the most massive open clusters in the entire galaxy, with an estimated mass between 30,000 and 50,000 solar masses and at least 26 confirmed red supergiant members. This concentration of evolved massive stars was remarkable. No other known cluster in the Milky Way contained as many red supergiants in one place. The cluster's age was estimated at 14 to 20 million years, and 01, placing it in exactly the right evolutionary window for stars of 12 to 16 solar masses to have left the main sequence and expanded into their red supergiant phase. But the real surprise was not the cluster itself. It was one particular star sitting at its outskirts. In the 2007 study, the brightest star in the region was given the identifier number 1, designated Stephenson 2 DFK1. However, the researchers immediately flagged it as problematic. The star sat at an outlying position relative to the cluster core. Its brightness was abnormally high compared to the other members. Its proper motion was slightly atypical, and its radial velocity, the speed at which it moved toward or away from Earth along the line of sight, did not quite match the rest of the cluster. Based on these discrepancies, Davies and colleagues categorized it as an unrelated red supergiant, a foreground or background object that happened to lie along the same line of sight as the cluster, but was not physically associated with it. In a separate study published in 2010, the same star was given a different identifier. Astronomer Shuji Deguchi and collaborators numbered it as Star 18, in a broader grouping of objects near the cluster, assigning it to a loose association called Stephenson 2 SWID, a collection of massive stars lying southwest of the cluster core that was assumed to be at a similar distance. The designation Stephenson 218, often abbreviated as Saint 218, comes from this numbering scheme. This dual naming, one star carrying two different catalogue numbers from two different studies, created confusion that persists in the literature to this day. The same object is referred to as Stephenson 2 DFK1, RSGC 218, and Stephenson 218 depending on which paper you are reading. The naming chaos is a small but telling detail. Even identifying this star cleanly requires navigating a tangle of overlapping catalogues and disputed associations. What made this particular star extraordinary was what happened when researchers calculated its properties using the cluster distance. Assuming Stephenson 218 sits at approximately 5.5 to 5.8 kiloparsecs, the same distance as the cluster, its apparent brightness translates into a staggering intrinsic luminosity. A 2012 study using the Australia Telescope Compact Array and a radiative transfer model called DUSTY derived a bolometric luminosity of nearly 440,000 times the luminosity of our Sun. Combined with an estimated effective temperature of approximately 3,200 Kelvin, this yielded a radius of 2,150 solar radii. But the 440,000 figure is not the only luminosity that has been published for this star. An older calculation from 2010, still assuming membership in the Stephenson 2 cluster at 5.5 kiloparsecs, but based on a narrower range of infrared flux densities at 12 and 25 micrometers, produced a dramatically lower estimate of only 90,000 solar luminosities. A newer calculation based on full spectral energy distribution integration at 5.8 kiloparsecs yielded an even higher figure of roughly 630,000 solar luminosities. That means published luminosity estimates for the same star at roughly the same assumed distance span a range from 90,000 to 630,000 solar luminosities, a factor of 7. Since radius is derived directly from the square root of luminosity at a given temperature, this spread implies vastly different possible sizes before the distance or temperature uncertainties are even considered. The 440,000 figure that produces the famous 2,150 solar radii is a middle value in this range, not a consensus. That number deserves a moment of stillness. 2,150 times the radius of the Sun. Our Sun has a radius of roughly 696,000 kilometers. Multiply that by 2,150, and you get a star with a radius of approximately 1.5 billion kilometers, a diameter of 3 billion kilometers. a volume roughly 10 billion times that of the Sun. If you could somehow hollow out this star and pour copies of our Sun inside like marbles into a jar, you would need 10 billion of them before the container was full. This is not a large star. This is not even a very large star. This is a star operating at a scale that breaks the relationship between the word star and any mental image a human being can form. The spectral classification added another layer of extremity. Stephenson 218 was typed as M6, an unusually late spectral type for a supergiant star. Most red supergiants fall in the range M0 to M4. An M6 classification corresponds to an exceptionally cool photosphere, and when you combine that extreme coolness with the enormous luminosity implied by the cluster distance, the result is a radius that sits well above what standard stellar evolution models predict as the theoretical maximum for red supergiants. That theoretical ceiling, known as the Hayashi limit, suggests that red supergiants should not be able to maintain stable structures beyond roughly 1,500 solar radii. Beyond that boundary, the star becomes fully convective and too unstable to sustain its envelope against the forces trying to tear it apart. Stephenson 218's estimated radius exceeds this limit by more than 40%. This tension between observation and theory is not a minor footnote. It is a fundamental problem. Either the measurement is wrong, the theory is incomplete, or something about this star's environment is producing misleading data. Each of these possibilities carries major implications. If the measurement is correct, and the star genuinely extends to 2,150 solar radii, it means our models of the maximum size a red supergiant can achieve need revision. If the measurement is wrong, it means the most famous giant star figure in popular astronomy is based on flawed inputs. And if the environment is distorting the data, perhaps through the thick dust envelope or circumstellar material producing an artificially cool spectral signature, then we are not measuring the star at all, but rather the material surrounding it. The scientific community did not immediately grapple with these tensions in a public way. What happened instead was more gradual and more familiar to anyone who watches how astronomical records enter popular culture. The number 2,150 solar radii appeared in papers. It appeared in databases. It appeared in comparison charts. It migrated from technical literature into Wikipedia articles, YouTube animations, and classroom posters. The caveats that accompanied the number in the original research, the flags about uncertain distance, doubtful cluster membership, and anomalous spectral properties were stripped away during this migration. What arrived in the public consciousness was a clean, confident claim. Stephenson 218, biggest star, 2,150 solar radii. Case closed. But the case was never closed. It was barely opened. To understand why, you need to appreciate how different this situation is from measuring something like the distance to the Moon or the mass of Jupiter. Those measurements are direct. We bounce laser beams off reflectors left on the lunar surface and time the return. We track the orbits of Jupiter's moons and apply Newtonian mechanics. The measurements are precise, repeatable, and tied to well-understood physics with small error bars. Measuring the radius of a star 19,000 light-years away in one of the most dust-choked regions of the Milky Way is an entirely different kind of science. You are not measuring the star. You are measuring the light that arrives at your detector after travelling for 19,000 years through a galaxy full of absorbing and scattering material. You are inferring the star's distance from the motions of other stars that may or may not be physically related to it. You are modelling the star's spectrum through layers of circumstellar dust that may be altering the signal in ways your model does not fully capture. You are estimating a temperature from spectral features that form in an extended, tenuous atmosphere, where the concept of a single well-defined surface temperature may not apply cleanly. At every step, you are making assumptions, and the final number you produce is only as reliable as the weakest assumption in the chain. For Stephenson 218, the weakest assumption is the distance, and the distance depends on whether the star belongs to the cluster. This is the hidden fault line running beneath the entire record holder story. If Stephenson 218 is a genuine member of the Stephenson 2 cluster, or at least sits at the same distance, then the luminosity calculation based on that distance is valid, and the derived radius, while extreme, follows from established physics. But if the star is not at the cluster distance, if it is a foreground red supergiant that happens to project onto the same patch of sky, then every property calculated from the assumed distance is wrong. A star that is closer than assumed would be less luminous than calculated. A less luminous star at the same temperature would have a smaller radius. The 2150 figure could shrink dramatically, possibly to something well within the normal range of large red supergiants, still impressive, but no longer record-breaking. The evidence on this question is conflicting. The 2007 study found the star's radial velocity to be offset from the cluster mean by roughly 20 kilometers per second. This is a significant difference. In a gravitationally bound cluster, members should share similar radial velocities. An offset this large suggests the star is either not part of the cluster or is moving through the cluster environment with an unusual velocity. The 2013 study by Verheyen and collaborators went further. Using silicon monoxide maser emissions and infrared carbon monoxide absorption features, they analysed the kinematics of red supergiants in and around the cluster and concluded that Stephenson 218 is a field red supergiant, unrelated to Stephenson 2. But the conclusion is not unanimous. Other researchers have pointed out that a 20 km per second velocity offset is within the range of typical outflow speeds for red supergiants with dense, expanding envelopes. If the star is losing mass at an extreme rate, and the evidence suggests it is, the expanding material surrounding it could shift the measured radial velocity away from the star's true systemic motion. In this scenario, the velocity offset is not evidence of non-membership, but rather evidence of an extreme mass loss episode. The star's unusual infrared excess, detected in multiple studies, supports this interpretation. Stephenson 218 displays strong infrared signatures of a thick circumstellar dust shell created by vigorous mass loss, including maser emissions that indicate extraordinarily high outflow rates. The possibility that the velocity discrepancy is caused by the star's own expanding envelope, rather than by physical separation from the cluster, keeps the membership question alive. Neither side has delivered a decisive blow. The star remains in a scientific limbo, not confirmed as a cluster member, not conclusively ruled out, sitting in an ambiguous space where its most famous property, its record-breaking radius, depends on which interpretation you choose to trust. This ambiguity is uncomfortable. Science prefers clean answers. Popular astronomy especially prefers clean answers, because clean answers make good graphics, good videos, good headlines. The biggest star in the universe is a powerful phrase. It fills screens. It fills thumbnails. It fills the imagination. But the reality behind that phrase is messier than any thumbnail can convey. The star that holds the most famous size record in modern astronomy is a star whose distance is uncertain by more than 50%. Whose cluster membership is disputed, whose spectral properties are anomalous, and whose estimated radius exceeds the theoretical maximum predicted by stellar evolution models. None of this means Stephenson 218 is ordinary. It is, by any reasonable interpretation, an extraordinary object. Even skeptical estimates place it among the largest and most luminous red supergiants in the Milky Way. Its mass loss rate is among the highest known for any star of its type. Its infrared brightness dominates its region of the sky. It is a dying giant surrounded by a shell of expelled material, burning through the final stages of its nuclear fuel before an inevitable collapse. Whether its radius is 2,150 solar radii, or something significantly smaller, it remains a star of staggering proportions and scientific importance. But the gap between extraordinary and record-breaking matters. It matters because the record-breaking claim is what made this star famous. It matters because the public understanding of this star is built almost entirely on the headline number. And it matters because the uncertainty surrounding that number reveals something important not just about this star, but about the entire enterprise of measuring the most extreme objects in the universe. What comes next will make the scale viscerally real. You will feel what 2,150 solar radii means when translated into the language of the solar system, the only frame of reference large enough to make a star this size even partially comprehensible. But it will also reveal why a star this bloated, this extended, this diffuse is fundamentally different from the compact, well-defined objects we picture when we hear the word star. The size is terrifying. What the size implies about the star's physical nature is even more so. Numbers do not frighten people. Not really. You can tell someone that a star has a radius of 2,150 solar radii, and they will nod politely, maybe raise an eyebrow, and move on with their day. The number is too abstract. It belongs to the same category as national debt figures and the age of the universe. Things you accept intellectually but never feel in your chest. To make Stephenson 218 real, you have to abandon the language of solar radii and translate the star into something the human brain actually recognizes. You have to use the only measuring stick large enough to make sense of an object this extreme. You have to use the solar system. Start with what you know. Our sun sits at the center of everything we call home. 8 planets orbit it. The 4 inner worlds, Mercury, Venus, Earth and Mars, hug relatively close, all of them contained within a sphere roughly 228 million kilometers in radius, the distance from the Sun to Mars. The outer planets, Jupiter, Saturn, Uranus and Neptune, spread across far greater distances. Jupiter orbits at roughly 778 million kilometers from the Sun. Saturn sits at about 1.43 billion kilometers. Rumor: these are distances so large that even light, crossing space at 300,000 kilometers per second, needs time measured in minutes and hours to traverse them. Sunlight takes about 8 minutes to reach Earth. It takes about 43 minutes to reach Jupiter. It takes roughly 79 minutes, more than an hour, to reach Saturn. Now, remove the Sun. Take it away. And in the empty space where it used to be, place Stephenson 218. The star's estimated radius is approximately 1.5 billion kilometers. Remember, this is the radius, the distance from the center to the surface. The surface of this star, its photosphere, does not simply nudge past the inner planets. It does not stop at Mars. It does not even pause at Jupiter. The photosphere of Stephenson 218, based on its most commonly cited size estimate, extends outward past the orbit of Saturn. Mercury is gone. Venus is gone. Earth is gone, swallowed so deep inside the stellar interior that its former orbit sits closer to the star's center than to its surface. Mars is gone. The entire asteroid belt is gone. Jupiter, the largest planet in our solar system, a world so massive it contains more matter than all the other planets combined, is gone. It would orbit not in the black vacuum of space but inside the body of the star, embedded within an atmosphere of incandescent hydrogen and other gases at temperatures of thousands of degrees. And still the surface keeps going, reaching outward until it approaches or crosses the orbital distance of Saturn, depending on which size estimate you use and how you define the outer boundary of the photosphere. Let that image settle. Every rocky world, every gas giant, every moon, every asteroid, every grain of dust orbiting our sun out to the distance of Saturn would exist inside this single star. Every world human beings have ever set foot on or landed a probe on, from the surface of the moon to the plains of Mars to the descent onto Saturn's moon Titan, would exist inside this single star. Even the mighty Cassini spacecraft, which spent 13 years orbiting Saturn, would have spent its entire mission inside the photosphere. Only the outermost planets, Uranus and Neptune, and the distant Voyager probes now drifting beyond the heliosphere would remain outside, orbiting in the darkness beyond the star's bloated edge. To grasp the sheer volume involved, consider what it means for one object to have a volume 10 billion times greater than another. Our sun is already vast. You could line up 109 Earths across its diameter. You could fit roughly 1.3 million Earths inside it. Now multiply that interior space by 10 billion. The result is a cavity so enormous that the concept of fitting objects inside it loses all intuitive meaning. You are no longer talking about a large sphere. You are talking about a region of space that dwarfs the distance between worlds. Light offers another way to feel the scale. A beam of light circling the sun at its equator would complete the trip in about 14.5 seconds. The sun is large by any human standard, but to light it is a brief sprint. Now send that same beam of light around the equator of Stephenson 218. The circumference of the star, based on the estimated radius, stretches to approximately 9.4 billion kilometers. Light, covering 300,000 kilometers every second, would need roughly 8 hours and 45 minutes to complete a single lap. You could wake up in the morning, send a photon racing around this star's surface, go to work, sit through meetings, eat lunch, handle the afternoon, and the photon still would not have finished its circuit by the time you sat down for dinner. A journey that takes 14 seconds around the sun takes nearly 9 hours around Stephenson 218. The star is so large that light itself needs the better part of a working day to trace its outline. But here is where the scale comparison begins to reveal something deeper than mere size. Because when you picture a star this large, your mind probably imagines a scaled-up version of the sun. A dense, blazing sphere with a well-defined surface, just bigger. That image is completely wrong. Stephenson 218 is nothing like a scaled-up sun. It is a fundamentally different kind of object, one that challenges what the word star even means at these extremes. Our sun is dense. Its average density is roughly 1.4 grams per cubic centimetre, slightly denser than water. Near its core, the density climbs to around 150 grams per cubic centimetre, more than 10 times the density of lead. The sun is a tightly packed ball of plasma, held in shape by the balance between the inward pull of gravity and the outward push of radiation pressure and thermal energy from nuclear fusion. Its surface, the photosphere, is sharply defined. There is a clear boundary where the solar plasma becomes transparent enough for light to escape. Below that boundary, the sun is opaque. Above it, the thin solar atmosphere gives way quickly to the vacuum of space. You can photograph the sun and see a crisp disk with a visible edge. Stephenson 218 has no such clarity. When a red supergiant expands to these extreme dimensions, its outer layers become extraordinarily tenuous. Imagine taking the mass of a moderately heavy star, perhaps 30 to 50 times the mass of the Sun, and spreading it across a volume 10 billion times larger than the Sun's. The resulting average density is almost unimaginably low. The outer envelope of a star like this is closer in density to a laboratory vacuum than to anything you would recognize as a solid or even a gas. You could pass through the outer layers of this star and barely notice a change in your environment. The material is there, hydrogen and helium plasma glowing at a few thousand degrees, but it is spread so thin that individual atoms may be separated by distances vastly larger than in any gas you have ever encountered on Earth. Imagine you could pilot a spacecraft toward this star from interstellar space. For a long time, there would be nothing unusual. Empty vacuum, cold and dark. Then, gradually, you would enter the circumstellar dust shell, the envelope of expelled material surrounding the star. You would not see a wall or feel a jolt. Your instruments would simply begin registering a faint increase in particle density, a thin haze of silicate dust grains and gas molecules drifting outward from the star at tens of kilometers per second. The dust would glow faintly in the infrared, warmed by the distant stellar radiation, but to your eyes the environment would still appear essentially empty. You could travel inward for millions of kilometers through this shell, and the change would be barely perceptible. The density would increase, the temperature would rise slightly, but you would still be flying through material far more diffuse than the thinnest wisp of smoke on Earth. Eventually, your instruments would register the photosphere, the nominal surface of the star, the depth at which the plasma becomes just opaque enough for photons to escape freely. But crossing this boundary would feel nothing like landing on a surface. There would be no ground, no wall, no sudden change. One moment you would be in the extended atmosphere. The next moment you would be nominally inside the star. The difference in density between just outside and just inside the photosphere would be negligible by any human standard. You would continue inward, and the density would keep climbing, but so slowly that you could travel for tens of millions of kilometers deeper into the star before the environment began to feel meaningfully different from the near vacuum you entered. The interior of this star, through most of its enormous volume, is emptier than any room you have ever stood in. Only far down, approaching the core, would you encounter densities and temperatures that match the popular image of a stellar interior. This extreme tenuity is what makes defining the edge of the star so difficult. The Sun has a photosphere you can point to and say, here is the surface. For Stephenson 218, the transition from star to not star is gradual. The density decreases smoothly as you move outward. At some point, the material becomes thin enough that photons can escape freely, and astronomers define that as the photosphere. But the exact location of this transition depends on the wavelength of light you are observing and the models you use to interpret the spectrum. At infrared wavelengths, the star may appear larger because the cooler, more extended material is more prominent. At shorter wavelengths, the star may appear smaller because you are seeing deeper into the hotter layers. This is not a technicality. It is central to understanding why measuring a star like this is so uncertain. You are not measuring a solid object with a defined boundary. You are measuring a gradient, a slow fade from dense plasma to thin plasma to circumstellar dust to interstellar space. Where you draw the line determines the radius you report. Different methods draw the line in different places, and the differences are not small. The reason this gradient exists, the reason the outer material is so diffuse and so weakly bound, comes down to a single physical quantity that is easy to state but staggering in its implications. The surface gravity of Stephenson 218 is extraordinarily low. Surface gravity depends on mass and radius. Increase the radius by a factor of 2,000, while holding the mass to perhaps 30 or 40 solar masses, and the gravitational acceleration at the surface plummets. On the Sun, the surface gravity is roughly 28 times what you feel standing on Earth. On Stephenson 218, the surface gravity is a vanishing fraction of that. A human standing on a hypothetical solid platform at the photosphere would weigh almost nothing. The gravitational pull at that distance from the star's centre, spread across so vast a sphere, is negligible by everyday standards. This feeble gravity has a direct and devastating consequence. The star cannot hold on to its own surface. Gas molecules in the photosphere move at thermal velocities determined by the local temperature. At 3,200 Kelvin, hydrogen atoms move at roughly 7 to 8 kilometers per second. On the Sun, this velocity is far below the escape velocity at the surface, which is over 600 kilometers per second. No thermal motion can overcome the Sun's gravitational grip. But on Stephenson 218, the escape velocity at the photosphere drops to under 100 kilometers per second. The thermal motions of the gas, combined with radiation pressure from the star's own luminosity pushing outward on every atom and dust grain, are nearly sufficient on their own to lift material off the surface. The star's atmosphere does not sit in comfortable equilibrium the way the Sun's does. It sits on the edge of escape, a reservoir of gas perched at the lip of a gravitational well so shallow that a modest push from convection, from pulsation, from a spike in radiation pressure, is enough to send material streaming into space permanently. This is why the mass loss is so extreme. It is not that Stephenson 218 is doing something exotic to expel material. It is that the star's own structure, its enormous radius, combined with its moderate mass, creates conditions where holding onto the outer layers is nearly impossible. The photosphere is not a stable boundary. It is a leaking membrane, constantly losing material to the circumstellar environment because gravity at that distance is simply too weak to contain a hot, luminous radiation-pressured atmosphere. Every pulsation cycle, every convective upwelling, every temporary increase in luminosity tips more material over the edge. The circumstellar environment makes things even more complicated. Stephenson, 218, is losing mass at a ferocious rate. Estimates place its mass loss rate at roughly 1.35 times 10 to the negative fifth solar masses per year. That means the star sheds roughly 4 to 5 Earth masses every single year, a river of material flowing steadily outward from the stellar surface into the surrounding space. Over the course of the star's red supergiant lifetime, which may span only a few 100,000 years, the cumulative mass loss is enormous. The expelled material does not simply vanish. It forms a dense, extended envelope of gas and dust surrounding the star, a cocoon of circumstellar matter that absorbs and re-emits radiation at infrared wavelengths. This dust envelope is directly detected in observations. Stephenson 218 displays a significant infrared excess, meaning it emits more infrared radiation than you would expect from the stellar photosphere alone. The excess comes from the warm dust surrounding the star, heated by the star's own radiation and glowing at longer wavelengths. Strong silicate emission features at 10 and 18 micrometers have been detected, indicating the presence of oxygen-rich dust grains in the envelope. Water masers, regions where water molecules amplify microwave radiation through stimulated emission, have also been detected around the star. Maser emission is a hallmark of red supergiants undergoing extreme mass loss because it requires the specific density and temperature conditions found in thick circumstellar outflows. The presence of this envelope raises a critical question. When we measure the star's apparent size and brightness, are we measuring the star itself, or are we measuring the star plus its surrounding material? If the dust envelope contributes to the observed flux in ways that the models do not fully account for, then the derived luminosity could be wrong. And if the luminosity is wrong, the radius is wrong. This problem is not hypothetical. It has happened before with other giant star candidates. WOHG 64, a red supergiant in the Large Magellanic Cloud, was once believed to have a radius approaching 3,000 solar radii. Then astronomers realized its surrounding dust was not a spherical shell but a torus, and radiation escaping through the cavity had been inflating the apparent luminosity. A single geometric correction cut the inferred radius nearly in half. We will return to WOHG 64 and other revised contenders later in this story, but the principle it illustrates applies directly to Stephenson 218. Any unmodelled asymmetry in the circumstellar dust, any geometric effect that channels radiation preferentially toward or away from our line of sight, could be distorting the luminosity we derive and therefore the radius we calculate. The star's thick dust envelope is confirmed. Its geometry is not. The same type of correction could apply to Stephenson 218. The star's spectral energy distribution has been described as somewhat peculiar. Published fluxes do not fit neatly within the accepted range of temperatures for red supergiants, and they do not conform cleanly to standard reddening laws. The models that describe how interstellar dust absorbs and reddens light at different wavelengths. These discrepancies suggest that the dust surrounding Stephenson 218 may have unusual properties or geometry that current models do not fully capture. If the true extinction is higher than assumed, the star would actually be even more luminous, which would imply an even larger radius. But if the circumstellar material is inflating the apparent infrared flux in ways that mimic a lower temperature or higher luminosity, the radius could be smaller than calculated. This uncertainty in the circumstellar environment connects to a deeper issue about what we are even looking at when we observe a star like this. A compact main sequence star like our Sun has a clean separation between the star and its surroundings. The stellar wind is modest. The surface is well defined. The spectrum reflects the conditions at a relatively thin photospheric layer, but for an extreme red supergiant, the boundary between star and surroundings dissolves. The photosphere is not a sharp surface, but a broad, fuzzy region where the density drops gradually and the temperature changes slowly with altitude. Above the photosphere, the extended atmosphere blends into the stellar wind. The stellar wind blends into the circumstellar dust shell. The dust shell blends into the interstellar medium. At no point is there a clean break. Astronomers sometimes describe these stars as resembling diffuse clouds more than distinct objects. The comparison is imperfect, but it captures something real. When you look at a star like Stephenson 218, you are looking at a vast, bloated mass of tenuous plasma, surrounded by an even vaster halo of expelled material, all of it glowing faintly in the infrared, all of it contributing to the signal your telescope receives. Extracting the properties of the actual star from this layered, extended source requires modelling assumptions that are difficult to verify independently. The mass loss itself is one of the most important and least understood aspects of extreme red supergiants. Stars lose mass throughout their lives, but the rate increases dramatically in the red supergiant phase. The mechanisms driving this mass loss are still debated. For moderately luminous red supergiants, radiation pressure on dust grains that form in the cool outer atmosphere is thought to be the primary driver. As the grains absorb photons from the star, they are accelerated outward, dragging gas with them through friction. But for the most luminous and extended red supergiants, additional mechanisms may be at play. Large-scale convective motions in the stellar envelope, which can produce convective cells half the size of the star itself, may intermittently lift material above the photosphere to regions where dust can form and radiation pressure can take over. Pulsations in the stellar envelope, driven by instabilities in the nuclear-burning shells deep inside the star, may also contribute by periodically compressing and expanding the outer layers. For Stephenson 218, the mass loss rate is among the highest observed for any red supergiant. This means the star is actively destroying itself. Every year, material equivalent to several Earth masses leaves the star and will never return. Over thousands of years, the cumulative loss reshapes the star's structure, stripping away outer layers and potentially exposing deeper, hotter regions. Eventually, this process may contribute to the star's transition away from the red supergiant phase entirely, possibly evolving toward a bluer state before its core collapses in a supernova. But before that final collapse, the star exists in a state of extraordinary tension. Gravity pulls inward, trying to compress the star. Radiation pressure pushes outward, trying to blow the envelope apart. Convection churns the interior, transporting energy from the deep nuclear-burning regions to the diffuse surface in rolling motions that may take years to complete a single cycle. The envelope pulsates, swelling and contracting over periods of hundreds or thousands of days. The balance between these competing forces is precarious. A star this extended is a star on the verge. It is not a stable, long-lived structure like a main-sequence star that can burn steadily for billions of years. It is a brief, unstable, terminal phase in the life of a massive star, lasting, perhaps, a few 100,000 years before something gives way. This instability is part of what makes the Hayashi limit relevant. The Hayashi limit, named after Japanese astrophysicist Chushiro Hayashi, describes a boundary on the Hertzsprung-Russell diagram, the fundamental chart that plots stellar luminosity against surface temperature. The limit defines the lowest effective temperature a star of a given luminosity can maintain, while remaining in hydrostatic equilibrium, the state where gravity and internal pressure balance each other throughout the star's interior. Stars cooler than this limit become fully convective and cannot sustain a stable structure. They sit in what theorists sometimes call a forbidden zone on the diagram. For red supergiants, the Hayashi limit translates into a maximum radius of approximately 1,500 solar radii. Beyond this size, the models predict that the star's envelope becomes too unstable to persist. The material either falls back inward or is expelled outward, but the star cannot remain in a steady state at that extended radius. Stephenson 218's estimated radius of 2,150 solar radii exceeds this theoretical ceiling by roughly 43%. Either the star has found a way to exist in a state that theory says is forbidden, the theory is missing something important about extreme stellar envelopes, or the measurement is wrong. Each of these possibilities carries weight. Theoretical models of red supergiants are known to be sensitive to assumptions about convection, mass loss, and the mixing length parameter, a tunable quantity that describes how efficiently convective cells transport energy. Small changes in these assumptions can shift the predicted Hayashi limit by hundreds of solar radii. It is possible that the actual upper boundary for red supergiant radii is higher than current models suggest, and that stars like Stephenson 218 are showing us where the real limit lies. Alternatively, the star may not be in true hydrostatic equilibrium at all. It may be in a brief, transient state of extreme expansion, a temporary bloating episode driven by an intense mass loss event, or a shell-burning instability that will not last long on astronomical timescales. Stars in such transient states can temporarily exceed theoretical steady-state limits because they are not in equilibrium. They are dynamically evolving. But the most straightforward resolution remains the simplest one. The estimated radius may be too large. If the distance is wrong, the luminosity is wrong, and the radius shrinks. If the temperature is even slightly higher than the 3200 Kelvin estimate, the radius shrinks further. If the circumstellar dust is contaminating the flux measurements, the derived luminosity may be inflated. Any combination of these effects could bring the true radius down from 2150 solar radii to something closer to 1500 or below, within the range predicted by theory and consistent with the sizes of other well-studied red supergiants. This does not diminish the star. Even at 1500 solar radii, Stephenson 218 would be among the largest stars in the galaxy. A star that size would still extend past the orbit of Jupiter. It would still have a volume billions of times greater than the Sun. It would still be a dying colossus in the final stages of massive stellar evolution, shedding material at a prodigious rate and heading toward a core collapse supernova that will scatter heavy elements across hundreds of light-years of interstellar space. The star is spectacular regardless of whether it holds the record. But the record is what made it famous. And the record is what makes the uncertainty so important. Because if you strip away the 2150 figure and replace it with a number 40 or 50% smaller, Stephenson 218 is no longer the biggest known star. It becomes one of several very large red supergiants jostling for position in a list where every entry carries similar caveats and similar error bars. The clean, dramatic story of the single biggest star dissolves into a murkier and more honest picture of a handful of extreme objects whose true sizes we have not yet pinned down. That murkier picture is exactly where the science lives. What follows will open the hood on the measurement itself, trace the chain of assumptions link by link, and show precisely why astronomers disagree about how much confidence to place in the famous radius. It will reveal that the question is not simply how big is this star, but rather how much do we really know about a dying object 19,000 light-years away, hidden behind dust, bleeding material into space, and sitting at the intersection of observational uncertainty and theoretical limits that even specialists find uncomfortable. Every measurement in science tells two stories. The first story is the number itself, the result, the headline, the figure that ends up on posters and in documentaries. The second story is how that number was obtained, what assumptions went into it, what could go wrong, how fragile the chain of reasoning really is. For most astronomical objects, the second story is boring. The methods are well tested, the error bars are small, and the result is trustworthy enough that nobody loses sleep over it. For Stephenson 218, the second story is the entire point. Because the most famous number associated with this star, the estimated radius of 2150 solar radii, is not a direct measurement. It was never a direct measurement. It is the output of a calculation that depends on three quantities, each of which carries its own uncertainty. And when you trace those quantities back to their sources, You find a chain of inference held together by one assumption so contested that entire research papers have been written arguing about whether it is justified. The chain works like this. To calculate the radius of a distant star, you need its luminosity and its effective surface temperature. Luminosity tells you how much total energy the star radiates. Temperature tells you how much energy each square meter of its surface emits. The Stefan-Boltzmann law connects these quantities. A star that emits a known total energy at a known temperature must have a specific surface area, and from that surface area you can derive the radius. The math is clean. The physics is well established. The problem is not the formula. The problem is the inputs. Start with luminosity. You cannot measure luminosity directly. What you measure is the apparent brightness of the star as seen from Earth, the amount of light that actually reaches your telescope after travelling 19,000 light-years through gas, dust, and the interstellar medium. To convert apparent brightness into intrinsic luminosity, you need to know two things. First, you need the distance. Luminosity drops off with the square of the distance, so a star twice as far away appears 4 times dimmer. Get the distance wrong, and your luminosity is wrong by the square of the distance error. Second, you need to know how much light was absorbed or scattered by material between the star and your telescope. This correction, called extinction, is particularly severe for Stephenson 218, because the star lies in one of the most heavily obscured regions of the galactic plane, deep in the Scutum Centaurus arm, where dust is thick and pervasive. The extinction towards Stephenson 218 is substantial. The star is essentially invisible at optical wavelengths. You cannot see it with a visible light telescope no matter how large your mirror is. It is detectable only in the infrared, where radiation penetrates dust more effectively. Correcting for this extinction requires modelling how much light the intervening dust absorbed and at what wavelengths. Different extinction models produce different corrections, and the circumstellar dust surrounding the star itself adds another layer of complexity. You must disentangle the interstellar extinction, caused by material between Earth and the star, from the circumstellar extinction caused by the star's own expelled envelope. If you underestimate the extinction, you underestimate the luminosity. If you overestimate it, you overestimate the luminosity. Either error propagates directly into the radius calculation. Now consider the distance. This is where the entire edifice becomes precarious. Stephenson 218 is too far away and too heavily obscured for direct parallax measurement. The method where astronomers observe the tiny apparent shift in a star's position as Earth orbits the Sun and use basic trigonometry to calculate the distance. Parallax works beautifully for nearby stars. The Gaia spacecraft has measured parallaxes for nearly 2 billion stars with extraordinary precision, but for objects embedded deep in the dusty galactic plane at distances of several kiloparsecs, parallax measurements become unreliable. The angular shifts are too small, the extinction is too severe, and the systematic errors overwhelm the signal. Instead, astronomers estimated the distance to Stephenson 218, indirectly by assuming it lies at the same distance as the open cluster Stephenson 2. The cluster's distance was determined through a method called kinematic distance estimation. This method works by measuring the radial velocity of the cluster stars, the component of their motion along the line of sight, and comparing it to a model of how the Milky Way rotates. Different distances from the galactic center correspond to different expected radial velocities, so by matching the observed velocity to the model, you can infer the distance. The 2007 study by Davies and collaborators measured the radial velocities of cluster members and derived a kinematic distance of approximately 5.83 kiloparsecs, with an upper uncertainty of 1.91 kiloparsecs and a lower uncertainty of 0.78 kiloparsecs. Translated into light years, this gives a distance of roughly 19,000 light years, but with an uncertainty range stretching from about 16,500 to over 25,000 light years. A 2010 study by Deguchi and collaborators derived a similar kinematic distance of 5.5 kiloparsecs using the average radial velocity of 4 cluster members. A 2013 study by Verheyen and collaborators refined the cluster's average radial velocity and derived a distance of roughly 6 kiloparsecs, approximately 20,000 light-years. These estimates broadly agree, but the uncertainty is enormous. The 2012 study that derived Stephenson 2.18's luminosity and radius used the 5.5 kiloparsec distance and explicitly noted that the uncertainty in the distance was greater than 50%. 50%. That means the true distance could plausibly be anywhere from roughly 3 kiloparsecs to 8 or more kiloparsecs. At 3 kiloparsecs, the star would be much closer and much less luminous than calculated. Its radius would shrink proportionally. At 8 kiloparsecs, it would be farther and more luminous, potentially even larger than the current estimate. A 50% distance uncertainty is not a minor caveat. It is a gaping hole in the foundation of the measurement, but this uncertainty assumes the star actually belongs to the cluster. If it does, then the cluster distance, imprecise as it is, provides at least a reasonable starting point. The cluster members share similar positions on the sky, similar radial velocities, and similar evolutionary states, all consistent with being a gravitationally bound or recently dispersed group at a common distance. Assigning the cluster distance to Stephenson 2.18 makes sense if the star is part of this group. If it is not, the entire calculation floats free, untethered to any reliable distance anchor. The evidence for membership is genuinely ambiguous. On one side, the star lies in the same region of the sky as the cluster and appears in infrared images alongside the other red supergiants. It was assigned to Stephenson 2.12, a loose grouping of stars southwest of the cluster core that is assumed to lie at a similar distance. Its spectral type, M6, is extreme, but not wholly inconsistent with the cool, luminous supergiants found in the main cluster. Its maser emissions, detected in both water and silicon monoxide lines, are characteristic of the most luminous and mass-losing red supergiants, exactly the type of star you would expect to find in a massive young cluster. On the other side, the star's radial velocity does not match. The cluster members have an average radial velocity of approximately positive 109 kilometers per second. Stephenson 2.18's radial velocity is lower by about 20 kilometers per second. This offset is the single most important piece of evidence against membership. In a gravitationally bound cluster, the velocity dispersion, the range of speeds among members, is typically only a few kilometers per second. A 20 kilometer per second offset places the star well outside the expected velocity range. The 2013 study by Verheyen and collaborators examined this discrepancy directly. Using silicon monoxide maser emission and infrared carbon monoxide absorption, they compared the radial velocities of red supergiants in and around the cluster and concluded that Stephenson 2.18's velocity was significantly different from the cluster mean. Their interpretation was straightforward. The star is a field red supergiant, a massive evolved star that happens to lie along the same line of sight as the cluster, but is not physically associated with it. It could be in front of the cluster, behind it, or at the same distance but unrelated. Without an independent distance measurement, there is no way to tell. But the counter-argument has not been dismissed. A radial velocity offset of 20 km per second is within the range of typical outflow speeds for red supergiants with dense, expanding circumstellar envelopes. When astronomers measure a star's radial velocity using spectral lines that form in or near the photosphere, they are measuring the motion of the star's surface material. If that material is flowing outward due to stellar wind or mass ejection, the measured velocity will be shifted away from the star's true systemic velocity. For a star undergoing extreme mass loss, like Stephenson 2.18, this shift could easily amount to 10 or 20 km per second. In this interpretation, the star's true velocity does match the cluster, but the expanding envelope creates an apparent offset. This explanation is plausible but not proven. Testing it would require measuring the star's radial velocity using lines that form deep enough in the photosphere to be unaffected by the outflow, or using independent distance indicators like parallax. Neither measurement is currently available with sufficient precision. The Gaia spacecraft, despite its extraordinary capabilities, has not provided a reliable parallax for Stephenson 218 because the star is too faint at optical wavelengths and too heavily extinguished for Gaia's detectors to measure its position with the necessary accuracy. Future infrared astrometric missions might solve this problem, but none are currently operational with the required sensitivity. The result is a stalemate. The membership question cannot be definitively resolved with current data. Different researchers interpret the same evidence differently. Some treat the star as a probable cluster member, or at least place it at a similar distance. Others treat it as an unrelated foreground or background supergiant whose derived properties are unreliable. Published papers reflect this disagreement. Some cite the 2150 solar radii figure as the best available estimate. Others describe it as likely unreliable due to the uncertain distance and temperature. A few recent syntheses have noted that the star's extreme properties, the radius exceeding theoretical limits, the anomalous spectral energy distribution, the disputed velocity, should collectively be treated as warning signs that the derived parameters may not reflect the star's true nature. This brings us to the temperature, the second input in the radius calculation. Stephenson 218 was assigned a spectral type of M6 based on its carbon monoxide bandhead absorption in the 2007 study, with a similar classification confirmed by Negaruela and collaborators in 2013 using titanium oxide spectral features. An M6 spectral type corresponds to an effective temperature of approximately 3200 Kelvin, making Stephenson 218 one of the coolest supergiants known. This temperature is problematic for multiple reasons. First, an M6 classification places the star below the Hayashi limit on the Hertzsprung-Russell diagram. Theoretical stellar evolution models do not predict stable red supergiants this cool. The star sits in a region of the diagram that models describe as forbidden for stars in hydrostatic equilibrium. Either the star is not in equilibrium, which is possible for a transient bloating phase, or the temperature is being measured incorrectly. But there is a second boundary the star appears to violate, one that is observational rather than purely theoretical. The Humphreys-Davidson limit, established by astronomers Roberta Humphreys and Chris Davidson in 1979, describes an empirical upper boundary on the luminosity of cool supergiants. When you plot thousands of observed stars on the Hertzsprung-Russell diagram, you notice something striking. The upper right corner of the diagram, the region corresponding to extremely luminous and extremely cool stars, is nearly empty. There appears to be a diagonal ceiling above which no stable cool supergiants are found. Stars that approach this limit from below are observed to become violently unstable, shedding material in eruptions and episodic mass loss events that prevent them from climbing higher. The Humphreys-Davidson limit is not derived from a theoretical model of stellar interiors. It is drawn from observation. It represents the actual boundary that nature appears to enforce. When you examine the claimed properties of Stephenson 218, the combination of its luminosity, estimated at roughly 440,000 solar luminosities, and its extremely cool temperature of 3200 Kelvin, the star falls in or very near the forbidden zone above this empirical boundary as well. It sits uncomfortably close to a region where no confirmed stable stars have been observed. This is a separate and independent red flag from the Hayashi limit problem. The star does not merely conflict with one theoretical prediction, it conflicts with an empirically observed ceiling that holds across thousands of studied objects in multiple galaxies. When a single measurement places an object in violation of two independent boundaries simultaneously, the probability that the measurement itself is the problem rises significantly. The difficulty with measuring temperatures of extreme red supergiants is well known in the field. The spectral features used to classify these stars, primarily molecular absorption bands of titanium oxide, form in the extended, low-density atmospheres that surround them. These atmospheres are not well described by simple models. convective cells that may span half the star's diameter create temperature inhomogeneities across the surface. The molecular bands that define the spectral type form at different depths and different temperatures. A star with a patchy surface, some regions hotter and some cooler, will produce a spectrum that looks cooler overall than the average temperature of the surface, because the molecular features are more sensitive to the cooler regions. Studies have shown that temperatures derived from titanium oxide lines in red supergiants tend to systematically underestimate the true effective temperature. If the actual temperature of Stephenson 218 is 3,500 Kelvin instead of 3,200 Kelvin, the derived radius drops significantly, potentially by several hundred solar radii. The spectral energy distribution compounds the problem. Researchers have noted that Stephenson 218's observed fluxes do not fit neatly with either the accepted temperature range for red supergiants or standard interstellar reddening laws. The fluxes appear to require either a peculiar extinction curve or unusual circumstellar dust properties. This mismatch suggests that the standard assumptions used to derive the star's temperature and luminosity may not apply cleanly to this object. The star's enormous infrared excess, created by its thick dust envelope, further complicates the modelling. If the dust emission is not properly separated from the stellar emission, the inferred temperature and luminosity could both be biased. All of these uncertainties converge on the same conclusion. The radius of 2,150 solar radii is not a firm measurement. It is a best fit estimate derived from a chain of inferences, each of which carries substantial uncertainty. The distance is uncertain by more than 50%. The cluster membership is disputed. The temperature may be underestimated due to systematic biases in spectral analysis. The luminosity is affected by uncertain extinction corrections and circumstellar contamination. Change any one of these inputs by a modest amount, and the radius changes dramatically. Change 2 or 3 simultaneously, and the result could be a star that is still impressively large but well within the range of other known red supergiants. No longer an impossible outlier, no longer in conflict with theoretical limits, and no longer the unambiguous record holder. To appreciate what this means for the biggest star title, you need to see how the same pattern has played out with other famous candidates. The story of UY Scuti is the most instructive example. For years, UY Scuti was celebrated as the largest known star, with a radius estimated at 1,708 solar radii, based on a 2013 study that measured its angular diameter and combined it with a distance of roughly 9,500 light-years. The number appeared everywhere, in textbooks, in size comparison videos, in popular articles. UY Scuti became synonymous with extreme stellar size. Then the Gaia spacecraft provided new parallax data. The Gaia Data Release 2 yielded a revised distance estimate for UY Scuti that was significantly smaller than the previously assumed value. A closer star with the same apparent brightness is less luminous. A less luminous star at a given temperature has a smaller radius. When astronomers recalculated UY Scuti's radius using the new Gaia distance, the result collapsed. Revised estimates dropped to somewhere between 755 and 909 solar radii, depending on the analysis, roughly half the original figure. In a single data release, the most famous giant star in popular culture went from the undisputed champion to a star comparable in size to Betelgeuse, far smaller than Mu Caffei, far smaller than VY Canis Majoris. The record was not just broken, it evaporated. The UY Scuti story carries a cautionary message that applies directly to Stephenson 218. The original radius estimate for UY Scuti was not careless or sloppy. It was published in a reputable journal based on careful angular diameter measurements. The problem was the distance. When the distance changed, everything changed. The same vulnerability exists for Stephenson 218, except that the distance uncertainty is even larger. UY Scuti at least had an angular diameter measurement. Stephenson 218 does not. Its radius is inferred entirely from luminosity and temperature, both of which depend on the assumed distance. WOH G64 provides another parallel. This red supergiant in the Large Magellanic Cloud was once estimated to have a radius as large as 3,000 solar radii, based on spectroscopic measurements that assumed spherical dust shells surrounding the star. When Very Large Telescope observations in 2007 revealed the dust to be shaped like a torus rather than a sphere, the geometric correction reduced the inferred luminosity dramatically. The currently accepted radius is approximately 1,540 solar radii, consistent with theoretical predictions for the most extreme red supergiants. In 2024, further observations by the VLTI directly imaged the dusty torus, and a study suggested WO G64 might have transitioned to a yellow hypergiant with a radius of only 800 solar radii. However, that interpretation was challenged in early 2026 by spectroscopic data from Jacco van Loon's team at Kiel University, which detected molecular absorption bands indicating the star remains a red supergiant after all. The anomalous observations were instead explained by the periastron passage of a binary companion whose tidal forces temporarily distorted the primary's outer atmosphere. The lesson from WOHG64 is that even stars, with relatively well-constrained distances in the Large Magellanic Cloud, whose distance is known to within a few percent, can have their radii revised dramatically based on improved understanding of their circumstellar environments. For a star like Stephenson 218, where the distance is uncertain by more than half and the circumstellar environment is known to be complex, the potential for revision is far greater. VY Canis Majoris offers yet another comparison. This red hypergiant in the constellation Canis Major was once estimated to have a radius as large as 2,200 solar radii. Subsequent measurements revised this downward to approximately 1,420 solar radii. Still enormous but significantly smaller than the original claim. The revision came from improved distance estimates and better modelling of the star's extended atmosphere and dust shell. VY Canis Majoris remains one of the largest known stars, but its history demonstrates the same pattern. Initial extreme estimates get revised downward as data improves. NML Cygni follows the same trajectory. Early estimates placed its radius as high as 3,700 solar radii. More recent values range from approximately 1,183 to 2,770 solar radii, a range so broad that the star could be either the largest known or merely one of several comparable giants, depending on which measurement you trust. The uncertainty reflects the difficulty of measuring a heavily obscured, mass-losing red supergiant embedded in a dense circumstellar nebula. The parallels to Stephenson 218 are unmistakable. Across all of these cases, a consistent pattern emerges. Extreme initial size estimates for red supergiants are almost always revised downward as better data becomes available. The revisions come from improved distances, better understanding of circumstellar geometry, refined temperature measurements, or corrections for systematic biases in spectral analysis. No major giant star candidate has ever been revised significantly upward. The trajectory is always the same. The first estimate is the most dramatic. Every subsequent measurement brings it closer to Earth. This pattern does not prove that Stephenson 218's radius will be revised downward, but it strongly suggests caution. The star exists in exactly the same observational regime that produced overestimates for UY Scuti, WOHG64, VY Canis Majoris, and NML Cygni. It shares the same vulnerabilities: uncertain distance, complex circumstellar environment, extreme mass loss, and spectral properties that challenge standard modelling techniques. The probability that its headline figure will survive unchanged as data improves is, based on historical precedent, low. The question then is what kind of observations could actually resolve the debate. Several concrete possibilities exist, and some of them may become feasible within the coming decade. The most transformative would be a reliable parallax or angular diameter measurement. The European Southern Observatory's Very Large Telescope Interferometer, VLTI, has already demonstrated the ability to resolve the angular diameters of red supergiants at significant distances. If the interferometric baseline could be applied to Stephenson 218 despite its heavy extinction, a direct angular diameter combined with any reasonable distance estimate would provide a radius measurement independent of the luminosity temperature chain. The extremely large telescope, currently under construction in Chile with a primary mirror over 39 meters across, will offer unprecedented resolving power in the infrared. Its adaptive optic systems are designed to cut through atmospheric turbulence and deliver diffraction-limited images that could, in principle, constrain the angular size of an extremely luminous infrared source at several kiloparsecs. On the distance front, future infrared astrometric missions could provide what Gaia cannot. Gaia operates primarily at optical wavelengths, which makes it blind to heavily extinguished objects in the galactic plane. A space-based infrared astrometry mission with micro-arcsecond precision could measure the parallaxes of obscured stars directly, bypassing the extinction problem entirely. Such missions have been proposed but not yet funded or built. In the nearer term, deeper spectroscopic surveys of the Stephenson 2 cluster region could help resolve the membership question by measuring radial velocities and chemical abundances for a larger sample of stars in and around the cluster. If Stephenson 218's chemical composition, particularly its ratios of heavy elements, matches the cluster members precisely, it would strengthen the case for membership even if the radial velocity remains offset. If the abundances differ, it would support the field star interpretation. Radio and submillimeter observations offer another avenue. The maser emissions from Stephenson 218's circumstellar environment carry information about the velocity structure and geometry of the outflow. Very long baseline interferometry at radio wavelengths could map these masers with sufficient angular resolution to distinguish between a symmetrically expanding envelope, which might explain the velocity offset, and a more complex geometry that would argue against it. Such observations are technically demanding but feasible with existing facilities like the Very Long Baseline Array. Until these observations arrive, the debate will continue. And the honest answer to the question of whether Stephenson 218 is the largest known star is not yes and not no. It is that the star is a leading candidate whose claim rests on assumptions that are reasonable but contested, and whose headline figure sits in tension with both theoretical predictions and the historical pattern of how giant star measurements evolve. What remains after you strip away the confidence of the headline number is something more interesting than a clean record. It is a genuine scientific mystery. Stephenson 218 is undeniably extreme. Its infrared luminosity dominates its region of the sky. Its mass loss rate is among the highest measured for any red supergiant. Its spectral type is unusually cool. Its massive emissions indicate extraordinary physical conditions in its circumstellar environment. Even without the record-breaking radius, this is a star that demands explanation, and the explanation is not straightforward. If the star is not a cluster member and sits at a significantly different distance, then its luminosity and temperature need to be recalculated from scratch. What kind of star produces this particular combination of observational properties at an unknown distance? If the star is a cluster member, but its radius truly exceeds the Hayashi limit, then stellar evolution models are incomplete. What physical process allows a red supergiant to expand beyond the theoretical maximum while remaining luminous and detectable? If the temperature measurement is biased by the extended atmosphere or circumstellar contamination, then what is the star's true effective temperature? And how do we measure it reliably when the star is invisible at optical wavelengths and surrounded by dust? Each of these questions leads into active areas of research where the answers are not settled. The physics of extreme red supergiants remains one of the less well understood chapters of stellar evolution, precisely because these stars are rare, distant, heavily obscured, and short-lived. They represent a tiny fraction of all stars in the galaxy. They exist in a phase that lasts only a few 100,000 years, and they tend to inhabit the most dust-choked regions of the galactic plane where observation is hardest. Building a statistical understanding of their properties requires finding and characterizing many such objects, and the current sample remains small. Stephenson 2.18 sits at the extreme end of this small sample. Whether it truly holds the record or not, it represents one of the most extreme data points we have for red supergiant properties. Understanding it correctly matters not just for ranking purposes, but for testing the theoretical framework that predicts how massive stars evolve, how they lose mass, how they die, and how they enrich the interstellar medium with the heavy elements necessary for planets and life. Getting its radius right is not about defending a title. It is about understanding the physics of the most extreme stellar objects in the galaxy. The final stretch of this story will pull back from the measurement details and ask what it means that the biggest star we know of is also one of the most uncertain. Not uncertain because astronomers are careless, but uncertain because the object itself exists at the ragged edge of what stars seem able to become, where the physics is hardest, the observations are most ambiguous, and even defining what you are measuring requires choices that different experts make differently. The terror of Stephenson 2.18 is not that it is vast. It is that it sits at a boundary where stellar physics, observational astronomy, and human intuition all begin to break down together. There is a moment in every great astronomical story where the facts stop being merely surprising and start becoming unsettling. Not frightening in the way of asteroid impacts or gamma-ray bursts, not threatening in any physical sense, but unsettling in the way that a cracked foundation is unsettling. You thought the ground was solid. You built your understanding on it, and then you look down and see the fracture running through everything you assumed was stable. Stephenson 2.18 delivers that moment, not through its size alone, but through what its size, combined with its uncertainty, reveals about the nature of the most extreme objects in the universe. The terrifying truth about the biggest known star is not that it might swallow Saturn's orbit. It is that the most extreme stars push both stellar physics and human measurement to their absolute limits. And what emerges from that collision is not a clean record, but a zone of genuine ignorance dressed up in confident-sounding numbers. To understand why this matters beyond the story of one particular star, you need to step back and look at what red supergiants like Stephenson 2.18 actually are. Not what they look like in artists' impressions or size comparison videos, but what they are physically. Because the popular image of a giant star, a vast glowing sphere sitting majestically in space, is misleading in ways that go far beyond aesthetics. It hides the most important thing about these objects, which is that they are dying. A red supergiant is not a star in its prime. It is a star in its final act. The story begins millions of years earlier, when a massive star, perhaps 25 or 30 times the mass of the Sun, ignites hydrogen fusion in its core and takes its place on the main sequence, the long stable phase where stars spend most of their lives. During this phase, the star is hot, blue, compact, and relatively well behaved. It burns hydrogen steadily, converting trillions of tons of hydrogen into helium every single second. The outward pressure from this fusion exactly balances the inward pull of gravity, and the star exists in a stable equilibrium that can persist for millions of years. But massive stars burn fast. A star 30 times the mass of the Sun does not live 30 times as long. It lives far shorter, perhaps only 6 to 8 million years on the main sequence, because the rate of fusion increases much faster than the available fuel supply. When the hydrogen in the core is exhausted, the equilibrium breaks. The core contracts under gravity, heating up until it ignites helium fusion. The energy released by the contracting core and the new shell of hydrogen burning around it pushes the outer envelope outward. The star expands. Its surface cools. It reddens. Over a period measured in thousands of years, the compact blue giant transforms into something almost unrecognizable, a bloated, cool, luminous red supergiant, with a radius hundreds or even 1,000 times larger than it had on the main sequence. This expansion is not gentle. It is driven by deep structural changes in the star's interior that propagate outward through the envelope in ways that are still not fully understood. The core becomes a dense, hot furnace cycling through progressively heavier elements, helium fusing to carbon, carbon to neon, neon to oxygen, oxygen to silicon, each stage shorter and more desperate than the last. The outer envelope, meanwhile, becomes a vast, diffuse, convectively churning ocean of hydrogen and helium that barely knows the core exists. The connection between the two regions is maintained by radiation and convection, but the timescales are so different that the envelope and the core evolve almost independently. The core races toward collapse on a schedule measured in thousands of years. The envelope drifts and pulses on timescales of centuries or longer. This disconnect between the frantic interior and the sluggish exterior is part of what makes red supergiants so difficult to model. The core physics is relatively well understood. Nuclear reaction rates are measured in laboratories. The equations of state for dense matter are constrained by particle physics experiments. The neutrino physics that will ultimately trigger the core collapse is complex but tractable. But the envelope physics is a different world. Convection in these stars operates on scales that dwarf anything in terrestrial experience. Individual convective cells can span half the diameter of the star, rising and falling over periods of months or years. These motions are turbulent, chaotic, and three-dimensional. They cannot be accurately captured by the one-dimensional models that form the backbone of stellar evolution theory. The standard treatment of convection in stellar models uses an approximation called mixing length theory. Developed in the 1950s, and still employed today because nothing better has proven computationally feasible for full evolutionary calculations. Mixing length theory describes convection using a single tunable parameter, the mixing length ratio, which sets the typical distance a convective element travels before dissolving into its surroundings. This parameter is calibrated against observed stars, primarily the Sun, and then applied uniformly across all stellar types. But there is no physical reason to expect that a parameter calibrated on the Sun should work for a star 2,000 times larger with a surface gravity millions of times weaker. The convective motions in a red supergiant are qualitatively different from those in the Sun. They are slower, larger, more irregular, and more coupled to the star's pulsational behavior. Using the same convective prescription for both objects is a known limitation, and it introduces systematic uncertainty into every prediction about red supergiant structure, including the predicted maximum radius. This is why the Hayashi limit, the theoretical upper boundary for red supergiant radii at approximately 1,500 solar radii, should be understood not as a hard wall but as a prediction with soft edges. The limit emerges from models that use mixing length theory to describe convection. If the true convective behavior in extreme red supergiants differs from what mixing length theory predicts, the actual limit could be higher or lower. Some researchers have argued that the Hayashi limit should be regarded as approximate, subject to revision as three-dimensional simulations of red supergiant convection improve. Others maintain that the limit is robust because it reflects fundamental thermodynamic constraints rather than the details of convection. The debate is unresolved, and Stephenson 218 sits squarely in the middle of it. The star's spectral type adds another dimension to this theoretical tension. At M6, Stephenson 218 is among the coolest supergiants known, sitting at or below the temperature range where stellar evolution models predict stable red supergiants can exist. This coolness is not just an observational curiosity, it has physical implications. A cooler photosphere means the molecular opacity in the outer atmosphere is higher, because molecules like titanium oxide and water form more readily at lower temperatures. Higher molecular opacity changes how radiation escapes the star, which in turn affects the thermal structure of the envelope and the balance between radiation pressure and gravity. At extremely cool temperatures, the opacity becomes so sensitive to temperature that small changes can trigger large structural responses. The envelope becomes what physicists call a tightly coupled system, where perturbations amplify rather than damp out. This sensitivity helps explain why extreme red supergiants are variable. Stephenson 218, like most red supergiants, is not constant in brightness. It fluctuates over periods of hundreds to thousands of days, brightening and dimming as its envelope expands and contracts. These pulsations are not the regular, clockwork oscillations of a Cepheid variable star. They are irregular, sometimes semi-periodic, sometimes chaotic, driven by the complex interplay of convective motions, opacity changes, and nuclear shell-burning instabilities deep in the interior. The star breathes, but it does not breathe steadily. Each cycle is slightly different. The amplitude varies, the period shifts, the star is not in equilibrium. It is constantly adjusting, constantly teetering, constantly negotiating the balance between the forces trying to hold it together and the forces trying to blow it apart. Mass loss is the most dramatic expression of this instability. Red supergiants shed material from their surfaces at rates that increase sharply with luminosity and radius. For the most extreme objects, the mass loss rate can exceed 10 to the negative fifth solar masses per year, meaning the star loses the equivalent of several Earth masses annually. Over the few 100,000 years of the red supergiant phase, this adds up to several solar masses of material expelled into the surrounding space. The expelled material forms circumstellar shells, clumps, and arcs that can extend outward for light years, creating complex nebular structures visible in infrared and radio observations. The driving mechanism behind this mass loss remains one of the major unsolved problems in stellar astrophysics. As we explored earlier, the combination of dust-driven winds, convective upheavals, and pulsation-driven ejections all contribute. But no single model fully accounts for the observed rates in the most extreme red supergiants. The rates exceed what standard wind models predict, sometimes by large margins. This gap between predicted and observed mass loss is not a minor calibration problem. It points to missing physics in our understanding of how the most luminous cool stars interact with their own envelopes. Some researchers suspect that the most dramatic mass loss events are not steady outflows at all, but episodic eruptions. Brief, violent episodes where a significant fraction of the envelope is shed in a single convulsive event, lasting years or decades rather than millennia. Stephenson, 218's extreme infrared excess and maser emissions suggest it has recently undergone, or is currently undergoing, an intense mass loss episode. The thick dust envelope surrounding the star absorbs a significant fraction of its luminosity and re-emits it at infrared wavelengths. The silicate features in its spectrum indicate oxygen-rich dust composition, consistent with the chemistry expected in the outflows of massive red supergiants. The water masers detected in the circumstellar environment require specific physical conditions, high densities, moderate temperatures, and velocity gradients that are characteristic of powerful stellar winds interacting with the surrounding medium. This mass loss is not just a spectacle, it is an existential process for the star. Every kilogram of material that leaves the surface reduces the star's total mass, weakening the gravitational pull that holds the remaining envelope in place. As mass decreases, the envelope becomes easier to expand, which lowers the surface gravity further, which makes it easier for radiation pressure to drive more material away. The process feeds on itself. The star becomes progressively less bound, progressively more diffuse, progressively more extended. It is not merely aging, it is evaporating. At some point this process will end, not gradually, but catastrophically. The core of Stephenson 218 is almost certainly in the late stages of nuclear burning, fusing elements heavier than helium in a sequence of increasingly brief and frantic phases. Carbon burning lasts a few thousand years, neon burning lasts a few years, oxygen burning lasts months, silicon burning lasts days. When the core has fused its way to iron, the sequence stops. Iron cannot release energy through fusion. Without an energy source to support it, the core collapses in less than a second, plunging from a volume the size of Earth to a sphere roughly 20 kilometers across. The resulting shockwave rips through the envelope and blows the star apart in a Type II supernova, one of the most energetic events in the universe. The supernova will scatter the star's remaining envelope across hundreds of light-years of interstellar space. Heavy elements forged in the core and during the explosion itself, carbon, oxygen, silicon, iron, and heavier elements created by the flood of neutrons during the collapse, will mix into the surrounding gas clouds and eventually be incorporated into new generations of stars and planets. Some fraction of the material in your body was once part of a star like Stephenson 218, a massive giant that lived fast, expanded beyond comprehension, shed its outer layers into space, and finally exploded in a death so violent it briefly rivaled the combined light of 1 billion ordinary stars. The calcium in your bones, the iron in your blood, the oxygen in every breath you take were forged in the interiors of massive stars and delivered to the interstellar medium through exactly the kind of supernova that awaits Stephenson 218. But before that final moment, the star exists in a state that challenges the very concept of what a star is. When most people hear the word star, they picture the sun, a dense, hot, sharply defined sphere of plasma burning steadily in the vacuum of space. Something solid enough to have a surface, something stable enough to last for billions of years, something discrete enough to be clearly distinguished from its surroundings. Stephenson 218 violates every element of that picture. It is not dense. Its outer layers are more tenuous than any vacuum achievable in terrestrial laboratories. It is not hot, at least not at its surface, with temperatures barely exceeding 3,000 degrees, comparable to the filament of an incandescent light bulb. It does not have a sharply defined surface. Its photosphere fades gradually into an extended atmosphere that blends into a circumstellar envelope that blends into the interstellar medium. It is not stable. It pulsates, convulses, sheds material, and fluctuates in brightness on timescales of months and years. And it will not last. Its red supergiant phase is a brief moment in cosmic time, a few 100,000 years out of a total lifespan of perhaps 8 million years. It is a transitional state, a dying gasp, a star in the process of ceasing to be a star. This is what makes the measurement problem so deep. You are not measuring a well-defined object. You are measuring a process, a phase, a transition. The star does not have a single radius in the way a planet has a radius. Its size changes with time as it pulsates and loses mass. Its apparent size changes with wavelength as different layers of the atmosphere contribute differently at different frequencies. Its inferred size changes with the assumptions you make about distance, temperature, extinction, and circumstellar geometry. The number 2150 solar radii is not a measurement of a fixed quantity. It is a snapshot of a moving target through a foggy window using a ruler that might be the wrong length, and yet the number matters. Not because it settles the question of which star is biggest, but because it forces us to confront what happens when we try to measure objects that exist at the absolute extremes of physical possibility. The history of giant star measurements is a history of successive revisions. Initial estimates revised downward, record holders dethroned, confident claims replaced by cautious ranges. UY Scuti went from 1,708 solar radii to under 1,000. WOHG 64 went from 3,000 solar radii to 1,540. VY Canis Majoris went from over 2,000 to approximately 1,420. NML Cygni remains uncertain by more than a factor of 2. Each revision reflects improved data, better modelling, and more careful treatment of the systematic uncertainties that plague these measurements. Each revision tells the same story. The most extreme initial estimates are almost always too large. Stephenson 218 has not yet undergone its revision. The 2,150 figure has persisted in the literature and in popular culture because no new measurement has definitively replaced it. But the conditions for revision are all present. The distance is uncertain. The cluster membership is disputed. The temperature may be systematically underestimated. The circumstellar environment is complex and not fully modelled. When better data arrives, whether from future infrared astrometric missions, improved spectroscopic analysis, or deeper surveys of the Stephenson 2 cluster region, the number will almost certainly change. The direction of the change, based on every precedent in the field, is likely to be downward. But here is the part of the story that deserves to outlast any particular number. Even if Stephenson 218's radius is revised to 1,500 solar radii, or 1,200, or even less, the star will still be one of the largest and most extreme objects in the galaxy. It will still be a dying colossus shedding its outer layers into space at a prodigious rate. It will still be approaching the end of its nuclear fuel supply and heading toward a core collapse supernova. And it will still represent a class of objects that sit at the boundary between what stars can be and what they cannot. That boundary is the real story, not the ranking, not the title, not the question of which particular star happens to measure a few hundred solar radii larger than its competitors on any given day. The real story is that the universe produces objects so extreme that even our best instruments and our most sophisticated models struggle to describe them accurately. The largest stars are not merely big versions of ordinary stars. They are qualitatively different objects, governed by physical processes that operate in regimes where our theories are least reliable and our observations are most difficult. They exist at the intersection of stellar evolution, convective physics, mass loss theory, dust chemistry, and observational technique, and at each of these intersections, the uncertainties compound. The fact that we cannot say with confidence which star is the largest is not a failure of astronomy. It is an honest reflection of how science works at the boundaries of knowledge. Clean answers exist in the middle of parameter space, where objects are well behaved and well observed. At the extremes, where the physics is hardest and the data is sparsest, certainty gives way to ranges, estimates, and competing interpretations. This is not a flaw. It is the signature of genuine exploration. The edge of knowledge is always fuzzy, and the most extreme objects in the universe live precisely at that edge. Stephenson 218 is terrifying, not because it might be the biggest star. It is terrifying because it represents a category of object that pushes everything we know to its breaking point. Stellar evolution models strain to accommodate it. Convective theories cannot fully describe it. Mass loss prescriptions cannot fully explain it. Observational techniques cannot fully resolve it. Distance methods cannot reliably place it. Even the concept of a stellar surface becomes ambiguous when applied to it. It is a star that exists at the ragged boundary of what the word star can contain. And out there in the Scutum Centaurus arm, buried behind thousands of light years of gas and dust, invisible to every optical telescope on Earth, Stephenson 218 continues to burn. Its core fuses ever heavier elements in a countdown that has no pause button. Its envelope swells and contracts in slow, irregular pulses. Its wind carries material outward at tens of kilometers per second, building a circumstellar tomb from its own substance. It does not know it is famous. It does not know that millions of people have watched videos declaring it the biggest star in the universe. It does not know that its most celebrated property is debated by the very scientists who study it. It simply exists, vast and unstable, quietly shedding itself into the dark, waiting for the moment when the last fuel is spent, the core surrenders to gravity, and the star that may or may not be the largest we have ever found announces its death in a flash of light that will outshine 1 billion suns. When that light reaches Earth, 19,000 years from now, no one alive today will be here to see it. The supernova will arrive as news from a star whose name we gave it, whose size we argued about, and whose true nature we never quite managed to pin down. The biggest star in the universe is not a settled fact written in stone. It is an open question written in infrared light across a dusty patch of the Milky Way, and the answer keeps changing every time we look more carefully. That is not a disappointment. That is exactly what makes the universe worth looking at. The most extreme objects in existence are also the most uncertain, and the uncertainty is not a gap in our knowledge. It is a window into the places where the universe operates beyond the limits of what we have learned so far. Stephenson 218 sits in that window, enormous, unstable, unresolved, and utterly magnificent.